the concept of paging, right? So in paging, in general, if you look into the main memory will be divided into some n number of parts, where each and every part we will call it as a frame with some size, right? And we are going to take a process. The process will be divided into n number of parts. That n number of parts will be depend on size of the page or size of the frame, in such a way that each page size should be equivalent to frame size, right? Fine. So have you observed one thing? We are introduced one terminology here called page table, right? Page table, which is managed by memory management unit. Do you have any kind of doubt that where will be the page table will reside? Where will be the page table will reside, right? Hope you understood. This is main memory, and this is a kind of a process, right? Process always might not reside in the main memory, that's for sure. Whatever thing that is required for us, that will be loaded into the main memory. Then what about the page table? Page table will always reside in the main memory, or it can be outside also, right? So just think about it. What is the functionality of page table? Page table will contains page numbers, n number of page numbers, and every page number is associated with one frame, frame 0, frame 1, frame 2, and so on, right? So which means that page table functionality is to identify my page is, let's say my page number 4 is available at which frame number. So always operating system will look for which one first? Page table. When operating system wants to look for page table, first it has to reside in main memory, right? So that you have to understand, right? Always page table has to reside in the main memory. Then where it will reside? In the main memory. In main memory, in one part. Am I right or not? So finally, how the structure will look like? If you look into the main memory, main memory is divided into multiple parts of same size, and some parts are occupied with operating system code. Am I right or not? Operating system code, because always operating system has to run, and some parts has to be run by some process 1, some parts has to be run by process 2, and some parts has to be run by some process, and so on. And some parts has to be definitely run by what? Page table. Definitely run by page table, right? So which means that if any one of these frames has to be executed, before that what it has to be executed? Page table. So first, where I am going to look into? Page table. Without looking into the page table, I am not going to enter into the main memory. Am I right or not? Right? So because logical address will be generated by the CPU, which it's known its own address. That address will be available in the hard disk. That is what we call it as the relocatable address. Right? To get the physical address, first I have to go for the page table. That page table address I will call it as base address. So I am going to have relocatable address. That relocatable address will be added with the base address, so that I can go for the page table. Once I go for the page table, I can able to know that it is fourth page. Then I can get frame 5, so I can jump into the frame 5. So you have to think that always page table is going to be reside inside the main memory. But here one concern will be there, right? So if I say here page size is 1 KB, page size is 1 KB, this is 1 KB and so on. So at the end this is also 1 KB, but there might be some situations where page table might be more than 1 KB. Is there any chance to get or not? At that situation page table also has to be splitted. Page table also has to be splitted, right? Suppose for example, if I say, try to calculate it, logical address is 22 bits, and page size is 4 kilobytes. Always it should be byte addressable. 4 bytes, 4 kilobytes, and offset will be 12 bits. Can you calculate number of pages? Okay. So if you are able to understand the concept, then you can able to solve any kind of question. How we are going to get the number of pages? Logical address space by page size, right? So logical address space is how much? 2 power 22 by 2 power 12, which is 2 power 10 pages, right? If it is 2 power 10 pages, then try to calculate what is the page table size. What is the page table size? If you want to calculate the page table size, so for each and every process there will be page table. In this page table, how many parts will be there? Total number of pages. Total number of pages are how many? 2 power 10 into each and every page table entry. What is the page table entry size now? They haven't given, right? Or can you able to calculate the page table entry now? If you want to calculate the page table entry, you have to definitely have physical address space. Is there any physical address space? No, right? So just note down, page table entry is assume page table entry will be 4 bytes, which is very minute, right? It's a kind of simple address, so which is very minute, 4 bytes. So 2 power 10 into 4 bytes. What is the value? 4 kilobytes. Is it equal to 4 kilobytes or not, right? So which means that is the 4 kilobytes page table size is enough to place in one page? Enough or not? My page table size is 4 KB. My partition size is 4 KB. Will it fit in one location or not? Yes, it fit. So that is the reason there is no problem with this particular kind of requirement. But if you look into some other kind of scenario where page table size is more than the page size, then what you have to do? You have to definitely split, right? So that is where you will get the concept of multi-level paging. So far we have seen only single level paging. We are going to get only one page table. That page table will reside in the main memory itself, right? Now there will be certain situations where page table will entirely will not fit in the main memory. At that situation, what will happen? For example, let us say logical address is 32 bits, and physical address is 2 power 44 bytes or whatever it might be, right? So I can say, okay, let me say 2 power 40 physical address space I can write, right? If I want to represent in the form of 2 powers, that will be entire space I am trying to say. In terms of address, I am going to represent in terms of bits. And page size will be 4 kilobytes. Then can you able to calculate number of pages first? Number of pages, simple, which is 2 power 32 by 2 power 12, which is 2 power 20 pages. 2 power 20 pages, right? If I am going to calculate 2 power 20 pages, can you able to calculate page table size, which is 2 power 20 into, you have to know page table entry. Assume that page table entry will be 32 bits, which means indirectly I am saying that 4 bytes. 34 byte, right? Now try to calculate what is the size of this one. 4 MB. 2 power 10 is KB, 2 power 20 is MB. 4 MB. So if page table size is 4 MB, can this 4 MB page table size can able to fit in the one page? Question is, this is main memory, which each part is 4 KB, 4 KB, 4 KB, 4 KB and so on. Assume that one page table is fit here, right? If you want to fit, does 4 MB is fit? No, which means 4 MB is far larger than the 4 KB. So definitely it is not possible. Then what you have to do? Again, page table has to be split into multiple parts in such a way that each part should be of 4 KB. Each part of 4 KB. Then how we are going to split it? So can I split this into again what size? In which size I have to split? Again 4 KB. 4 KB means what? 2 power 12. Have you understood, ma? 4 MB is not at all enough for us to place in the one place. Now what is my requirement? How I can able to fit this entire page table? If I am going to split this entire 4 MB process into small part. What is the small maximum part size? Page size, which means 4 MB by again 2 power 12. 4 MB means what again? So which I can write it as 4 KB, right? 4 KB, 4 cancel. 1 MB by 1 KB, which is 2 power 10. 2 power 20 by 2 power 10, which is again 2 power 10, which is equal to 1K pages. 1K pages. I mean, what you are getting here, try to observe. As my main page table is not able to fit, I have again further split it. If I further split it, again I got 1K pages. So in terms of system, this is again a kind of a process or not? Again a process. For this process, again I have to maintain one more page table. If I am going to maintain this is one page table, then how many number of pages will be there? 1K pages, and each page is what? 4 bytes. I have mentioned already. Assume 32 bits is the page table entry. That can be anything, right? 1K page into 4 bytes, which is equal to what? 4 KB. Does now 4 KB is able to fit into one process, one page size? Yes. Right. By luckily, we got here 4 KB by using one level of partitioning. It will be placed here. There will be certain situations where this is also not possible to fit. Then what you have to do? Again we have to move further. That is what we call it as multi-level paging, right? So this is what page table 1. Page table 1 size, this is 1. This is what? Page table 2. Page table 2, right? So what I am trying to say here is, if I say this is the main memory, in this main memory I am trying to fit one page table here, but if I want to work with this entire remaining part, if I want to connect to this one, I have to create one page table, amma. Hope you understood. I have to create one page table. But unfortunately, if I am going to create one page table to convert logical address into physical address, it has got the size of what? 4 MB. But this 4 MB couldn't able to accommodate here. For that reason, what I did, if I want to accommodate, I am going to create one page table. That page table you got as 4 MB. Now, this page table, again I am going to be split it. So that it will be fitted, and you got the size as 4 KB, right? Which means this entire thing is not able to fit here. Hope you understood. Now what is the meaning of this one? This is page table level 1, or I can call it as inner page table. Technical terminology may modify inner page table, and this will be outer page table, or I can call it as page table 2. Page table 2, right? So here how many parts are there? 1K parts. Each part of size 4 bytes. That's why it is equal to 4 KB. Here this is how many parts? Each part is 4 KB, 4 bytes, and but how many parts will be there? 2 power 20. 2 power 20, right? Now think about how the main memory will occupy. In the main memory, is page table 2 will be stored or page table 1 will be stored? Page table 2, right? Page table 2 will be stored in the main memory. Good. So CPU will generate logical address. Along with the logical address, it is going to generate what? Base address of page table 2. Base address of page table 2. Hope you are understanding, right? Base address of page table 2. Once I got the base address of page table 2, I will get to this location. Which means that this entire thing. Now already CPU generated what? Logical address. Logical address generate chesindi ante, which contains what? Offset along with page number. Right? Which means that some page number it is generated. Let's say 5. Which means that I will go to the page number 5. In this page number 5, what it contains? Frame number, right? So this is connected to certain frame number. This is frame number. But think about it. Is it a page table 1 or page table 2? Page table 2. If it is page table 2, which is connected to a frame number, so this is what now? Is it actual data or a part of the page table? Good. Part of page table, right? Means there will be certain part, that part is loaded here. This part is loaded here. This part is loaded, right? Once you come to this location, again it contains what? Frame number. Am I right? Again it contains frame number, so that it will be connected to the next one. Am I right? Again it will be connected to the next one. Now here is what? Data. So to get this data, what you require? Offset. Have you understood? So this is the working of multi-level paging. So this procedure is what? 2-level paging. As I am going to have 2 page tables, this is 2-level paging. 2-level paging, right? In 2-level paging, how the logical address will be? That is the next question. In 2-level paging, how the logical address will be? So what you required first, tell me. Anyhow, for any kind of thing, what is the minimum requirement? Offset is definitely required, and base address anyhow you will get, right? So if I get the base address, then only I will come to here. After getting the base address, I have to have page number. What is that page number? If it is like multi-level paging, 2-level paging, outer level page number you are going to get. So that I will come to here. Then I will come to this location. Right? Now here the data will be there. That data will be referenced with another page number. Right? So that this will come to this location. Okay now. So which means, so again you might get confused. This is entire one page size. Here it's not the single page number. Which means indirectly it's a collection of many things. Have you understood? Just think about this one. This is a 4 MB size. If I am going to divide into 4 KB parts, if each one is 4 byte, how many things we will get? Half of the things. Half the things will be one part and half the things will be one part. Now hope you understood. This half of the thing will be equivalent to this part. Am I right? This half of the thing will be equivalent to this part. If half of the thing will be equal to this part, out of this half of thing, if you want to go to again one thing, again you require one page number. One page number, so that you can come here and then it will be connected to the respective thing. See, I will try to explain once again. Try to listen. One minute. I am going to have main memory. As per the example, I have calculated something page table 1. Page table 1 size is what? 4 MB. In general, here each page can able to accommodate 4 KB, right? So I am trying to represent that 4 MB also here. This is 4 MB. Each size is 4 bytes. Why it is each size is 4 bytes? This is page table. And each size is 4 table. And how many things will be there here? How many pages are there? 2 power 20 pages are there. 2 power 20 pages are there, right? So because of this thing, as it is reaching to 4 MB, I couldn't able to accommodate its place. Right? As I couldn't able to accommodate its place, I have to split this one. How we are going to split this one again? Again of page size. If I am going to split into page sizes, what will happen? 4 KB. For 4 KB, how many pages you are going to get here? 1K pages. Try to calculate. How you got that? 2 power 20 into 4 bytes, or page table 2 we are going to calculate 4 MB by 4 KB. 4 MB 4 KB, you are going to get 1K. So which means that 1K pages you are going to get for page table 2. 1K pages. Each size is 4 bytes. So finally you are going to get 4K. Right? So just think about it. CPU generated some logical address. That generated logical address will contains at the end our final data. Right? This thing I will call it as what? Offset. Total page size, if you convert into bits, that will be the offset, right? So this will be the definitely offset, right? But if you want to come to this location, you have to cross many things, right? What is that? You have to come to first page table 2. So to come to the page table 2, as this is entirely fit here, I can able to accommodate PT2. As I get the base address, I can reach to here, right? In this PT2, how many pages are there? 1K pages are there again, right? Out of these 1K pages, you have to move to which page? That will be defined by logical address, right? So out of these many pages, it will generate, let us say, 5. Means what? Page number 5. So you required one page number. So this is outer page number. So I come to the, let us say this is the page number 5, right? So as I reach to the page 5 of PT2, what I will get my here? 4 bytes. 4 bytes means what? Address of another thing. What is the address of another thing? What it will contains? it will be connected to some PT1, into some PT1, right? So that some PT1 is what? Again, it will be divided into parts or not? It will be connected to parts, right? So as PT1 is split into many things, so 1k parts, right? So this is available in some way, right? Now it is connected. Now if it wants to connect to this one, again assume that this is the part that was loaded as PT1 somewhere. Part of PT1. I am trying to write clearly. Part of PT1, not the exact one, right? So if you want to come to this location, that will be defined by which one here? It was already defined. So once I reach to page 5, I can connect it to this page, which means I can come to this page. Good. But if you go with the part of PT1, again how many pages will be there? Many pages are there. To come out of with this many pages, again what you have to do? Again you have to know which is the page number I have to go. Which is the page number. So for that, here you have to have required inner page number. Once you get the inner page number, I can go to the respective page number, so that it will contain some certain frame number, so that I can connect like this. So which means what? If I am going to have 2-level paging, how many page numbers you have to mention here? 2 page numbers. If I am going to have k level paging, k page numbers will be having, along with that offset will be there, right? So now the question is, what is this value? How we are going to calculate this values? Right? So just tell me with the same values. Let's say logical address will be 32 bits and physical address space will be to power 44 bytes. Page size will be 4 KB and page table entry will be 4 bytes or 32 bits. Fine, this is the data. Now we have to calculate the exact page numbers. How we are going to calculate the exact page numbers? Right? Anyhow, as per the understanding, the main memory is divided into how many parts? 2 power 32 parts. Why 2 power 32 parts? 2 power 44 by 2 power 12, which is 2 power 32 frames. Main memory contains 2 power 32 frames. And when you are able to calculate, you got the page table 1 size as what? 4 MB. And when you are going to calculate the page table 2, you got the size as 4 KB, so that page table 2 can able to fit here. Right? So to work with that, page table 2 base address you are going to get. So what I am trying to say here is, when you have a CPU knows some base address, let us say some thousand, right? So when it knows some thousand, it can directly reach to the respective location. Once it reaches to the respective location, it has to find page number. In page to which page number you have to go? How many possibilities are there? You already have page table 2. In order to uniquely identify each and every page, how many bits are required? It contains how many pages? 1k pages. If I am going to have 1k pages, how many bits are required? 10 bits are required. If I am going to have 10 bits, I can able to identify one page uniquely. That's the reason, which is 10 bits. Right? once I know this one page, I will move to which location? The respective frame number. Right? In this respective frame number, again it was split into how many? Multiple parts, right? So that is related to which one again? Again page table 1. Right? Now try to think, what is this value I have to place? See, this is of size what? 4 KB. This is of size what? 4 KB. In 4 KB space, how many same page table size can be placed? 1K pages only. Am I right or not? Here 1K pages are already directly fit. Here 1K page fit. If 1K pages are fit, out of 1K pages, if you want to uniquely identify, how many bits are required? Again 10 bits. Right? So out of 1K pages, 1 page you identified and the respective frame number you got, and you will go to the respective location. Then here it is a page size. Page size is what now? 4 KB. Out of 4 KB, if you want to identify uniquely one, how many bits are required? 12 bits. 12 bits, right? So this is offset. This is inner page table 1. I can write page table 1. This is page table 2. Somewhat complex here. Try to understand. Is it okay? Fine. So this is the logical address that is generated by the CPU. So total how many bits are there? Total 32 bits which is generated by the CPU, which is equivalent to this. Okay now, right? So try to solve some of the questions so that you can get the clear idea. Let us say virtual address is 48 bits. Try to calculate, and page size will be 16 kilobytes. 16 kilobytes. Page table entry will be 4 bytes. Page table entry will be 4 bytes. Can you calculate what is the level of paging? What is the level of paging required? I mean, whether it is 2 level or 3 level, like that. And try to calculate the logical address also. What is the level of paging? What is the logical address? Right, try to understood. Just you have to make it some kind of illusion. That's it, right? So first thing is you have to calculate page table size. If you want to calculate the page table size, what you require? Number of pages, right? So try to calculate the number of pages first. What is the number of pages? 2 power 48 by 2 power 26. Is it 16k? Which is 2 power 14, right? 2 power 14. Okay. So number of pages will be how many? 2 power 34. If number of pages are 2 power 34, so what will be the page table size? PTS. 2 power 34 into what is the page size? 4 bytes. Then what will be the size of this one? 2 power 36 bytes. If 2 power 36 bytes, which will be equal to 64 GB, right? So anyhow, uh, two square, 2 power 36, right? 2 power 64 GB or MB? GB. Good, right? So try to observe. So this is page table 1. Page table 1 size is 64 GB, but actual page size is what? 16 KB. Will it sufficient? No, definitely it is not, right? So I have to further divide the page table 1 into multiple parts. If I want to divide the page table 1 into multiple parts, let's say page table 1 64 GB. I can work with directly like this: 2 power 34 into 2 square bytes by again 2 power 14. Again I am trying to split. If I am trying to split, what is the value? 2 power 20 into 2 square bytes, which is 4 MB. Am I right? Which is 4 MB. This 4 MB is also far larger than the 16 kilobytes, right? So which means that this is the page table 2 size. As page table 2 size itself is not fit in the one frame, again I have to move further, right? Which means page table 2, which is 2 power 20 into 2 square bytes by, again I have to split, which is 2 power 14, which is equivalent to what value? Two power 8. So 2 power 8. Why KB 2 power 8? This is page table 2, right? 2 power 8 pages. 2 power 8 pages. 2 power 8 pages, right? So then if you want to calculate the size, 2 power 8 pages into 4 bytes. 2 power 8 into 4 bytes means what? Which is 2 power 10 bytes. 2 power 10 bits, which is 1 KB. Is the calculation correct? Right, so try to observe here. Is it correct? 1 KB, right? So this is what page table 3. Does page table 3 is sufficient for us? Yes. Okay, now if page table 3 is sufficient, then you have to say how many levels are there? 3 levels: page table 1, page table 2, page table 3. So 3 level paging is required. Now, okay, fine. Then how about the logical address you are going to calculate? Tell me. Okay, calculate. What is the values you are going to get in the logical address? What is the offset anyhow? Offset can you able to calculate directly? Yes. What is the value? 14. Offset is definitely 14. Okay. Then, so then remaining how many fields you have to calculate? 3 fields. What is the first field value? Page table 3. How many parts are there? How many parts are there? 1k parts. If 1k parts are there, how many unique ways you can give? Using 10 bits you can give. So 10 bits are there. Is it okay? Everyone, 10 how I have written? Okay, fine, good. Then what about the values of page table 2 and page table 3? What is the value of page table 2? Same 10 you are going to get. Just think about it. I think it is not. Right? In the next level, what will happen is page size will be 16 kilobytes and each and every address will be 4 bytes. Then how much size it will be? 2 power 12. Okay na? 2 power 12. Right? So how many pages are there in the page table 2? 2 power 12. That is what you calculated, right? 4 2 power 12, right? If 2 power 12, how we are going to get uniquely one thing? 12. What about page table 3? Which is same again, 12. So this is the entire logical address. So which is equivalent to again I think 48. Okay, now try to find out. Right? So here the outer page table number of pages will vary, but inner page table pages will always equal. Why? Always the same page size with same division. So that's why inner page levels definitely will be of same number of bits are required, but outer page might be vary. But luckily earlier example both are same. Now this example will be. Right? If you want to have the clarity, try to solve one more question for the coming class. If virtual address is 64 bits and page size is 1 MB, page table entry will be 4 bytes. Then what will be the answer for this? Calculate it or will you calculate later? Right? First thing is we required what? Number of pages. Good. Number of pages. Number of pages is what? 2 power 64 by 2 power 20. Right? Which is equal to 2 power 44 pages. Right? So which is equivalent to, so can I write the clearly? Number of pages in page table 1 is 2 power 44. That should be multiplied with what? 4 bytes, which is equivalent to some larger value. Some larger value. Try to calculate which is also required, right? 2 power 46 bytes. Okay, let it be. Right? As 2 power 46 bytes is far larger than the 2 power 20 bytes. 1 MB means 2 power 20, right? 2 power 20 bytes. I will go for further splitting. How I am going to split further? So number of pages in page table 2, which is 2 power 44 into 4 bytes by 2 power 20, which is equal to 2 power 26 pages. See, some situations you have to write the pages and some situations you have to write the bytes. Right? Here it is bytes. It is 2 power 26 pages. Right? Then what is the size of the page table? 2 power 26 into 4 bytes, which is 2 power 28 bytes, means 3 MB I think. 2 power 20 into 2 power 8. Sorry, into 8. Right? So total 3 MB. So the 3 MB is larger than 2 power 20, 1 MB. Yes or no? Yes. That's the reason we are going to split further again. So what is the number of pages in page table 3? 2 power 26 into 4 bytes by 2 power 20, which is equal to 2 power 6 into 4 bytes, 2 power 8, 2 power 8 bytes. 2 power 8 bytes means which is equal to 2 power 8 bytes, right? That in bytes it is enough, right? So what is the level of paging now? 3 level: page table 1, page table 2, page level 3. Then can you able to calculate the logical address? So you already know what is the offset. What is the offset? Offset is 1 MB. If it is 1 MB, how we are going to get it? 20. Then here you require 3 parts. What is the first part? Page table 3. Out of 2 power 8 pages, number of pages, right? This is pages sum. Out of 2 power 8 pages, to uniquely give the naming for each and every page, how many bits are required? 8 bits are required. Then what about the inner level? Right? So inner level, one page size is what? 1 MB. What is the page table entry? 4 bytes, which is equal to 2 power 18. 2 power 18 pages are there. When 2 power 18 pages are there, 18 bits are required, and next also 18 bits are required. So 8, 18, 18 and 20, which is equal to 56 and 64, right? Which is equal to 64. Is it okay? So like this you have to calculate, which is very, very important in the grid. Is it okay with everyone? Okay. So similar kind of thing, try to solve it. I am going to give for you page size, which is 4 KB. Page table entry will be 4 bytes. Outer page table size 4 KB. Outer page table size is 4 KB, and level of paging will be 1. Level of paging will be 1. What will be the virtual address space? Right? Just controversy earlier to this one contracts. So what you required here now? They have given the outer page table size. Outer page table size is what? 4 KB. 4 KB. If the outer table size is 4 KB, how many entries will be there here? How many entries will be there? How can we calculate? So each page table entry size is what? 4 bytes. 4 bytes. If each page table entry is 4 bytes, 4 KB by 4 bytes is 1K. Right? Which means, what is the meaning of it? There will be 1K frames are there. Have you understood? If page table contains 1K entries, frame also contains 1K entries. Each page table entry will be connected to one frame. So 1K entries will be there. 1K entries will be there, right? And if 1K entries will be there, each entry size is what? 4 KB. Idamma page size kada 4 KB. Then 1K into 4 KB is what? What is the value? 2 power 10, 2 power 20, 2 power 22 bytes. So which is equal to 4 MB physical address space, not the logical address space, right? So the value of the physical address total memory size is 4 MB. Have you understood? Right? If I am going to have one page table, that one page table contains n number of entries, so that each entry will be connected to one frame, right? So if you are able to calculate how many frames it is connected and each frame size, you can able to calculate, right? As we got 1k pages, 1k entries will be definitely there, each entry will be 4 KB, so which is equal to 4 MB. So the physical address space size will be 4 MB. So to make it more clarity, let us say page size is 4 KB. Page table entry will be 4 bytes. Outer page table size is 4 KB. 4 KB. Level of paging will be 2. Level of paging will be 2. What will be the physical address space? Level of paging is now 2. Tell me. Then just think about it, how many references it is connected, that's it. So just check with, if I say outer page table is 4 KB, how many entries will be there? 1k entries. 1k entry, right? These 1k entries will be connected to which one? Direct frames or another page table? Another page table, right? So means which is connected to one page, which is connected to one, which is connected to one, which is connected to one, like that, right? So now if you are able to calculate how many pages are there here, how many pages are there here, can you able to get the main size, main page size, main memory size, right? Here how many frames, how many pages will be there again? Again the 4 KB by 4 bytes, which is again 1k, which means outer page table is 1k size, 1k pages. In each and every inner page table page also contains 1k pages. Then what will happen? One k into, so this is 1k and each will be connected to 1k. 1k into, have you understood that illusion? That this is page table 2, page table 2, which definitely contains 1k entries. This will be connected to not all, only one part of the page table 1 will be connected, right? So this is a part of page table 1. Part of page table 1 contains how many pages again? 1k pages. So now this one part will be connected to main data, right? So you have to think here how many things will be there, that many number of frames will be connected. So which means I can say these are 1k into these 1k connected like that into 4k. 1k into 1k into 4k. This is the size of the physical address space. So which is equal to what? 4 GB. Am I right? 2 power 30. If you take the 4 common, 4 aside, 2 power 3 2 power 10, 2 power 30 will be GB. So 4 GB is the answer. GB is the physical address space. Okay na? next month, right? Virtual memory is something like a kind of logical address only, logical memory only, right? Which means for the user basically will get an illusion if some process size is very larger than the main memory size, then the virtual memory concept comes into the picture, right? So it just generates a kind of illusion to the user. What is that illusion? More memory is there, right? So in general, how this virtual memory concept is going to work, right? Try to think. If I say this is the main memory, so in general you are trying to load page table 1, or let's say O means outer page table. Outer page table definitely will be there. Now there will be definitely some situations, let me call this outer page table as PT1 assume, or PT2, right? And PT1 definitely loaded somewhere, right? PT1 definitely loaded. So that PT1 is entirely loaded or part of it? Part of it will be entirely loaded. But there will be some situations where PT2 page addresses and PT1 page addresses will be collided. Is there a situation it is possible? Right? So it is possible because it is address, let us say 1, this address is 1. So that is address situation, what these frame numbers will contain, like 0, 1, 2, 3 and so on, they are going to maintain process number and page number. Process number along with the page number they are going to maintain, which means that process 1 page 1, process 1 page 2, process 2 page 1, process 2 page 2. If we are not going to maintain any process related thing, then it will get a confusion whether this P1 is related to process P1 or process P2. To avoid that confusion, they are going to maintain this kind of thing, right? So if you look into majorly this page table 1, so page table contains what? Exactly, compulsory minimum frame numbers will be there. In addition to frame numbers, we are going to have again valid or invalid bit. Right? Earlier concept we discussed page table entry, right? We know generally page table entry will contains frame number. Similarly, if you exactly look into the page table, it not only includes the frame number, it also includes various other kind of factors. One will be either valid or invalid, another one will be dirty bit, another one will be a reference bit, another one will be protection. These might be the various kind of factors. So if you say valid or invalid bit, which means that the page what you are looking for is available or not, is available in the main memory or not, that will be defined by the valid or invalid bit. I mean, the looking page is available in the respective frame, I can say it as 1. The available data or available page is not available in the respective location, it will make it as 0. Valid means 1, invalid means 0, right? So which means page is present or not. I can go for valid or invalid. And if the page is present, dirty means what? Whether it is modified or not. If it is not modified, it won't be done anything. If it is modified, that has to update back into the main data, main location. And reference means in the earlier clock cycle whether it is already referred or not, right? If it is already referred, what will happen? Instead of going for cache memory, instead of going for main memory, can we go for cache directly or not? That's the meaning of reference. If it is reference, that will be 1. If it is not reference, that will be the 0. If it is not reference, it will go to the main memory. If it is reference, it will go to the cache memory. Next one, production. Production bit means basically some users having some rights, right? Whether they are going to have write permission or not. Basically, everybody is going to have read permission, right? So certain kind of permissions will be defined in the form of production bits, right? This is the general structure what the page table is going to be followed. Okay. So here the point is when you are trying to move from page table 1 to page table 2, page table 2 to page table 3 and so on, is it going to be take some time or not? Yes or no? But the main thing here is why we are coming into this concept of either paging or virtual memory, to avoid external fragmentation. To avoid the external fragmentation, we are coming into the concept of paging, page table, or I can say virtual memory, like that, right? But whether we know or knowingly or unknowingly, we are making burden on ourselves. What is that burden? Page tables, right? For each and every splitting, we need to maintain one page table. That page table also might occupy some space. So that's the thing, right? So for that reason, there will be many problems will be there. What is that? One will be the memory accessing time. Memory accessing time, what will happen? Will be doubled. Why it will be doubled? How many times the memory is going to be accessed? See, in this particular example, memory accessing, how many times? 3 times. Why 3 times? First it is accessing for page table 2. Next, once you got the address, again it has to access for page table 1. Once it got the address, again it has to access for data, right? So 3 times you are accessing, which means that if I say some m seconds it is accessing for each and every time memory access, how many times it is time? 3m seconds or 3m nanoseconds, based on the factor what they are giving, right? So I can say in other words, if there will be a main memory, and some page table 1 is placed here. First, to access once CPU generated logical address, to access first page table 1, we need m nanoseconds or m seconds. From once you got the frame number, again you need to access the main memory. Again you have to go with the m nanoseconds or m second, right? So then what will be the total time? I can call it as effective access time. Effective access time is 2m. So this is for what level of paging? One level. First it has to access the page table, and then it has to access the main memory. So 2m time it is going to be taken. If I am going to have 2 level paging, 3m. If I am going to have k level page table, k, right, k plus 1 times of time it is going to be taken. On an average, which I can say it as km times, right? So is there any situation where we can reduce this accessing time? Can you go with that? Right? So because of every time you are accessing the main memory for m time, every time you are accessing the main memory, it requires m times. Right? If it is one level of paging, For page table 1 you required m times, for main memory accessing you required m times. That's the reason you are going to get 2m times. Is there any situation where can you able to place instead of placing the page table in the main memory itself to avoid m times of accessing, can we able to place some kind of memory elements like registers, so that this might take very less time compared to main memory accessing? Yes, this might be the solution. But what will be the page table size? Okay, here in this particular thing, accessing time they can be reduced, but registers are very small and they are too costly. And what about the page table sizes? They are too large. So page table sizes are too large compared to registers, so registers are not the best approach. That is the reason we are moving for another concept called TLB, or in general words we can call it as a catch. TLB, transition Lookaside buffer, or I can call it as associative memory, right? In TLB or associative memory, time taken to access a particular thing will be very less compared to main memory. That's the reason we are preferring for TLB. And the cost of the registers is far larger than the cost of the TLB. These are the two consequences why we are moving for TLB. Right? What is this TLB? TLB means it's a kind of a memory. Where each and every memory element is associated with some kind of tag. This tag is something like a kind of a key. Okay, so whenever CPU generates certain kind of logical address, so this logical address will contains what? Page number along with certain kind of offset. So whenever this page number is matched with any one of the key, something like that. Whenever this page number is matched with any one of the key, immediately it is going to give what? Frame number. So anywhere you have accessed the main memory here. See, this is main memory. So far we are trying to place the page table entirely inside the main memory. That's the why main memory accessing time is more. Entire processing is more. Now what I did, instead of placing the page table inside the main memory, I taken out and I placed in an TLB, transition Lookaside buffer or associative memory. So the reason is that, let us say, time taken for accessing the TLB is t seconds and time taken for accessing the main memory is m seconds, in such a way that t size of time is far less than the m. Based on this assumption, based on this condition, I am saying that this approach is better one. Right? So immediately now, here also I am trying to look for page table. But here the page table is available which location? TLB. That's the reason it is far less time accessing compared to the main thing. So now it will be connected to this. Is it okay? Anyhow, always all the data is not going to be available in the TLB. There might be some data which might not be available. Then what I have to do again? I have to go for the page table. See, page table is as usual. Earlier concept is as usual. Try to think. Earlier concept page table is as usual. In order to reduce the accessing time, I made a duplicate of it and I am trying to place in the TLB. First I will go for checking in the TLB If it is not available, then I will go for page table. Anyhow, at the end we have to come back. But majority of the cases, user is trying to check for always frequently accessing item. So based on that, I can say this is the better approach. See, for example, if I say, let's say OS faculty, somebody is there, right? Generally, OS faculty is available in the K3, assume, right? Always you are looking for inside the K3. If he is not available, you will go for HOD office. If he is not available, you will go for newsbit, right? Infrequent, he is always available in the K3, right? That is where accessing is, right? So based on this, TLB is the best, right? So hope you understood, right? Try to think as when user is searching for certain data in the TLB, if it is matching here itself, if it is success, I can call it as a TLB hit. TLB hit, it means what? Success. TLB fail means the data is not available here, then what I have to do? I have to go for page table. That is what I can call it as a TLB miss. TLB miss. I mean, I am going to generate one formula. So effective memory access time in terms of this TLB concept is, one will be TLB hit, and or it might be possible what? TLB miss. Either of the cases is possible. When TLB hit, assume that TLB accessing time is 20 nanoseconds, this T is 20 nanoseconds, this M is 100 nanoseconds. Then what will happen? This is 20 nanoseconds. If it is available 20 nanoseconds, anyhow, even if it is accessing 20 nanoseconds, again I have to go for which one? Main memory. Am I right or not? This will just provide only frame number. Again, if you want to look for my data, I have to go for the respective main memory, right? So which means 20 nanoseconds plus 100 nanoseconds. This is for what? TLB hit. This is not possible for all the cases. Some situations where it might fail. When fail, what will happen? TLB miss, okay. For that, what time it is wasting? 20 nanoseconds it is wasting. Why 20 nanoseconds it is wasting? For searching here, 20 nanoseconds wasting. After wasting this 20 nanoseconds, where I have to go? I have to go page table. In order to access the page table, how many nanoseconds it is wasting? 100 nanoseconds. After going to the page table, again it has to go to the main memory. This thing, right? So this is for TLB hit and this is for the TLB miss. Assume that on an average 80% is TLB hit ratio. I mean, out of 100 times, 80% of the times always TLB hit success rate. Means out of 100 times, 80% of the times user is always frequently accessing times, that is 80%, and 20% of the time is always accessing miss rate. Then what will the answer? Just calculate it, which is I think around 140 nanoseconds. But if you go with the general approach, always how much time is it going to take? For each and every access, it is going to take 200 nanoseconds. So on an average, how much time it is going to take? 200 nanoseconds. Is it okay? So this is the approach, you are going to get 140 nanoseconds. But in the earlier approach, every time you have to go with the page table and you have to go with the main memory. So this is for one request. For n request, always 200 nanoseconds only. By n, on an average. N cancel, you are going to get 200 nanoseconds. So 140 nanoseconds is far less than the 200 nanoseconds for a smaller part. If you go with the larger values, that will make huge impact also, right? So accessing the data with respect to the TLB or associative memory is the best approach compared to without TLB. Is it okay? Right? Based on that, can we generate the formula? If I say TLB hit ratio probability probability of TLB hit ratio is p%. P. Then can you calculate the formula? And TLB access time is T. Access time is T. Main memory access time is M. Then what is the formula for it? Effective memory access time equal to TLB hit ratio p%, right? P into, if it is success rate, success possibility aithe, then what you are going to access? TLB plus M. This is success rate. If it is fail, 1 minus P into, anyhow we have to access the TLB, then you have to access the main memory, page table, and then you have to access the main memory. Right? This is for one page level. If you look into the K level paging, you are going to get the probability P into T plus M plus 1 minus P into T plus Km. Page table 1, page table 2, page table 3 and so on, Km plus M. This is the formula for effective memory access time for all the things. Have you understood? Right? So, hope you understood. So, you might think that 140 nanoseconds is somewhat less than the 200 nanoseconds. But when you go with the N level paging, definitely you are going to reduce many things. Right? So, that is the reason. Right? So, just note down one question. In a paging schema, it uses, in a paging schema uses TLB. A paging schema uses TLB. The TLB access time is 10 nanoseconds. The TLB access time is 10 nanoseconds. Main memory access time is 50 nanoseconds. Obviously, main memory access time is more than the TLB access time. Okay. What is the effective memory access time? If TLB hit ratio is 90%, what is the effective memory access time if TLB hit ratio is 90%? If TLB hit ratio is 90%, calculate it. Right? If they haven't given any levels, you can go with the one level. Right? So, good question. If they haven't given any levels, you can go with the n levels. I think that point is required here. No. Okay, you required it. Right? So here you required assume that it is one level of page. Good mark. Right, calculate it. So what will the answer? 65. Right, simple. Effective memory access time. I am not going to write any formula. What is the hit ratio? So okay, good. I can directly write as 0.9 into 10 nanoseconds for TLB plus 50 for main memory, right? And for the failed case, 0.1 into TLB access time wasted and page table access and main memory access, right? Why they haven't given the page table access time? Because page table is reside in the main memory, right? So you can calculate it, you will get the answer as 65. Okay, fine. Then can you define any relation between effective memory access time and TLB hit ratio or miss ratio? Good, right? So which means when the TLB miss rate increases, what about the effective memory access time? Increases or decreases? Increases, because here the values are larger, right? Right, when the TLB miss rate increases, effective memory access time is also increases. TLB hit rate increases, effective memory access time decreases in point 1, right? So you might not always get TLB hit ratio in the gate questions. You might get sometimes TLB miss rate also they will give, right? Something like if I say TLB access time is T, TLB access time is T, main memory access time is M, access time is M, they might give TLB miss ratio is P, right? Earlier I have given the TLB hit ratio as P, right? If I give now TLB miss ratio as P, formula will vary, right? Try to calculate it, right? So if miss ratio is P, what is the formula? T plus, okay, first I am trying to write the miss ratio. If miss ratio T into T plus M plus M, okay, plus success ratio I am trying to write 1 minus P into T plus M. Calculate it, you are going to get something like T plus M plus P into M. Right? The earlier formula is different, this formula is different. Anyhow, don't by heart it, just solve them later part, there itself. They will be cancelled. Right? If it is K level paging, effective memory access time equal to T plus M plus P into K. They have given here the miss ratio. Earlier slide they come up with hit ratio. So here also they thought that there will be some problem. What is that means? That concept we are calling it as demand paging. Demand paging. So what is the meaning of demand? Based on the need. Based on the need, we are going to load the page, right? So demand paging means we can say that don't load any page, don't load any page until required, which means does you require any page table now, right? I am going to have main memory and this is going to have some parts. If I am going to load anything, I have to maintain in the page table, right? As I am not going to load anything, I am directly loading into, if it required, into the main memory. Is there required anyone in the middle? No need, right? So here to reduce the time accessing, anyhow we are going to go with the TLB. So this will look like this, right? this will be connected to this one. So there is no page table here, right? So when you are required any something, when you require something, if it is matched, it will go to the respective frame. It will go to the respective frame. If it is not matched, it will directly go to the main memory. It won't go for the page table at all. Why page table is removed here? Because we are always thinking about the needed one only. If it is frequently accessing, they will be loaded anywhere in the. See, earlier I said already, this is what a page table. This is what also a page table, but which contains a part of the page table, and that too is a dummy data, right? Why we are going to making a copy again unnecessarily? That is where this page table concept is removed here, right? So this is what we call it as demand page. Based on the need, we will load it. That's it, right? So if you are able to write the formula, what is the effective memory access time then? If hit ratio is P, hit ratio is P, or let us say this is a page fault. Means what? Hit miss. I mean a TLB miss. If it is miss, what is the meaning of page fault? The page what we are looking is not available. Not available, we can call it as page fault, right? If TLB miss is P, then what will be the formula? I have to go with the TLB access, then I have to go with the main memory. No need of. Anyhow, I have to go with the main memory at the end. I have to go with the main memory, right? If this page fault, if it is success, I have to go with the directly main memory. This is what we call it as a demand paging. Okay, now. So we are going to not going to load any pages until it is required, right? When it is success, I will directly go for the main memory. Otherwise, I will go for the TLB, then main memory. Based on that, try to note down one question. Right, so you might get some confusion. This is page service time, not the TLB success time. Page service time we can call. Page service time means the page what we are looking is not available for us, then time taken to load it requires T time. Page service time is T, and then it will go for the main memory. If it is success, I will directly go for the main memory. Okay. So note on the question. Let the page fault service time be 10 milliseconds. Service time is 10 milliseconds in a computer with average memory access time. Average memory access time is 20 nanoseconds. Okay. So, if one page fault occurred or generated for every 10 power 6 memory accesses. 10 power 6 memory access. If one page fault occurred for every 10 power 6 memory accesses, then what is the effective memory access? What is the effective memory access time? Just think about it. See, this is not the correct diagram. This is purely some other concept. The meaning is we are going to have purely only main memory, and we are not going to maintain any extra burden for us. Okay, now simply when you are trying to search for a page, if it is not available, then trying to get it from the hard disk will take certain time. That is what we call it as a page service time. Then I will look into the main memory, right? If it is available there itself, I will go for directly accessing the main memory. Okay, now so demand paging concept is purely different from the earlier concepts. Okay, now so that diagram is the wrong one. Try to note down normal thing, right? We are just simply, right, in the afternoon I will take certain frames so that you can get the clear idea, where I will take one empty data. I will take empty data. I am not going to load anything. Whenever I needed certain data, if it is not available, I will try to get it from the main secondary memory and I will place it. For that time it will require, we call it as page service time. Once I placed it, I will try to access it. I require memory time. So that is what page fault. If page fault happens, page service time will be there and main memory access time will be there. If it is success, means there itself there, then I go for main memory. Hope you understood now clearly. Is it okay? Fine. Now calculate it. The same formula, I can just simply substitute. What is the page fault service time here? 10 milliseconds. 10 milliseconds the page fault service time. Page fault service time is 10 milliseconds plus average memory access time is what? 20 nanoseconds. If one page fault is occurred for 10 power 6 memory access, which means what? 1 by 10 power 6. This is a page fault rate. 1 by 10 power 6, right? Otherwise, if it is success, 1 minus 1 by 10 power 6 into memory access time, 20 nanoseconds, right? Try to calculate it. Right? So you are going to get around 30 nanoseconds. You can calculate it. Everything will be converted into nanoseconds. Okay, na? So what is demand paging? Simple. I am not going to make any burden on us. We are going to have just simply main memory with empty. Whenever I am looking for a data, if it is not available, I will load it. We call it as page service time, and then I am going to access it. That is called memory access time. If it is success, I will directly access it. Next concept, inverted page table. Inverted page table. So, which means in general, if I am going to have n processes, I am going to have n page tables. It might take almost maximum 5 minutes. Okay. If I am going to have n process, I have to look for n page tables. Okay. So out of these n page tables, there might be certain pages where you might not be useful for us. We are not going to be used. Right. So suppose for example this is process P1, page table 1. This is page table 2 and so on. In page table 1, I have unused memory space of these 3. In page table 2, I have unused memory space of these three, right? Like that, it might be many page tables are there, right? If you combine together, again it is going to be memory wastage or not. Instead of that, they come up with certain proposal, that is what we call it as a inverted page table. In inverted page table, instead of having one page table for each and every individual process, we will have one page table for all processes. That's it. This is a simple one. Instead of maintaining individual page table for all individual process, I am going to maintain one page table for all process. Then you might get many doubts, right? How they will rectify the collision, all those things, right? If I say this is an inverted page table, earlier what we maintained, for one process one page table is there. For page table 1 there will be one process. If I say here 0 1 2 3 4 5 and 6, 0 1 2 3 4 5 and 6, like that is going to maintain. Now in inverted page table, to avoid the collision, so hope you got the clarity why collision will occur, right? Because page table 1 of 1 will collide with page table 2 of page 1, right? To overcome that, what they thought is they are going to maintain inverted page table, where this inverted page table contains number of pages equal to number of frames of the main memory. When it is equal to number of frames of the main memory, definitely collision is going to be avoided. Why? In one frame, only one respect to page table data only will be available, right? So here, how many pages are there, which is equal to number of frames of main memory, and they are going to maintain clearly process 1, page 3. These are the frame numbers, not the page numbers now. What are Mingus 1? In frame 2, process 1, page 3 is available. But earlier case of page table, if I say 1, some frame 3, like that, this is what page 1, this is what frame 2. In inverted page table, this index is frame. In normal page table, index is a page. That you have to observe, right? So based on this inverted page table, what will be the advantage? Space is going to be reduced, but anyhow there will be drawbacks, right? The drawback is, again, time will be increases, access time is going to be increased. Okay, now fine. Based on that, note down one example, one gate question only. If I say physical address is 32 bits, page size is 4 kilobytes, inverted page table entry is 4 bytes. Hope you understood. If I say some page table, every page table having page table entry. If I say inverted page table also having some page table entry, right? Because it is connected to, again, main memory, its address, right? So inverted page table also having inverted page table entry. What will be the size of inverted page table? Simple, very good. Number of frames into inverted page table entry size. But earlier case, what is the size of the page table? Means number of pages into page table entry. Here, number of frames into inverted page table entry size. So what is the number of frames? To power 32 by 2 power 12 into 4 bytes. Good. So which is equal to 2 power 20 into 4 bytes, which is 4 MB. Right? Have you understood this one? Right? Inverted page table concept is simple one. Right? Instead of pasting the memory space for each and every page table, I am going to combine all the page tables into one page table. We can call it as inverted page table. Okay. And what about the demand paging? Right? Instead of wasting the memory for the TLB or page table, I am going to directly go for main memory. That's it. Okay, we can stop here. We'll continue the next class.